Just this last name, first initial.
Hello, everyone. Thanks you for joining, whether in person or online. So we are about to start this last session of this great workshop. And this session will be about simulated LSST data. Starting from DP0, which is the official big simulation, but trying to go behind DP0 to see what we can do before the survey starts. So we have some speakers. I will start with a very brief introduction so that we can go straight to the point. So this session is was proposed by me and Sara Bonito online. I'm last year.
Can you do something about an echo on this side of it?
Just a minute.
Use your computers if you have.
Okay, so this session was proposed by myself and Sara Bonito, who's online. I'm a last year PhD student in Napoli, Italy. And before to start, remind that we have a code of conduct. So please attain to this code of conduct. If you report any violations, you can report this to these people here. And also please pay attention to name tags and stickers that are on badges of people. And this is an hybrid meeting. So for people online, we are monitoring both Zoom and Slack. So you can ask questions there. And you can also raise hand via Zoom and we can give you the word. And for people in the room, please remind that this side of the room has microphone. So if you want to ask a question, please come to discuss. So as a starting point, as I said, when talking about LSST simulations, DP0 is the very first thing to say. Now, I suppose you know very well what is it. This is a slide from last year prepared by Melissa Graham. So it was released 3 years ago now. And the scope of DP0 was to enable the community with something to test the Rubin Science Platform and to prepare science with LSST. So the main data set of DP0 is the Wood-Vasey simulations prepared by the Dark Energy Science Collaboration. So it is composed of simulated images over 5 years. And it contains many sources, clusters, galaxies, type 1a supernovae, stars. And there are also sources that are not included in the simulation. And so this is why the community was trying to make an effort to include those sources. And recently, last year, DP0.3 was added to the simulation. And it is a compilation of catalogs prepared by the Solar System Science Collaboration, including solar system objects. And there is plenty of resources to learn how to use DP0. And here I think is a great moment to thank the community science team because they're still doing something incredible to enable the community to use the data because they prepared wonderful tutorials. They are organizing the official DP0 assemblies, but you can join and you can ask questions. There is the community forum where you can ask for help. There is a very broad documentation that is still ongoing and improving, and the Rubin Science Platform that is accessible on data.lsst.cloud. But beyond this, the TVS Science Collaboration also organized a task force specific to DP0, which was active, especially when DP0 was first released. And the idea was to prepare notebooks or portal tutorials specifically focused on time domain science. And we have our own Slack channel that you can find on the LSST Slack space. And we are arranging telecons, and sometimes we also ask for breakout rooms during the dedicated DP0 assemblies. And the goals were to increase the TVS participation, but also other science collaboration participations into the DP0 effort for time domain oriented science. And we also reached some achievement because we presented some tutorials as delegate contributions, and some of us also participated and contributed into the DP0 Data Academy. Now, I want to stress that with all the goals and all the tutorials that we prepared, we touched almost all the goals and all the topics in the TVS roadmap that you can find at this link. Now, I will present you just very briefly a list of things that were done within this collaboration. And the first thing that I want to highlight is the importance of the education activity that you can reach with DP0. And for instance, there was this presentation given by Alessandro Salvatore Tramuto, that is an undergrad student in Palermo in Italy, that was supervised by Sara Bonito, and he presented a very nice portal aspect on the application of DP0 with young stellar objects, and he was also working with the notebook aspect tutorial. So it is extremely important to use this data with undergrad students that are approaching astronomy for the first time. And we tested different scientific applications. Here, for instance, there was a notebook prepared by Massimo D'Allora on the analysis of stellar variability with several algorithms to measure periodicities. There was a notebook with the investigation of young stellar objects using structure function, which is a method that usually it is used for AGN, but it can be used to pick up variability with sources with a typical rate noise trend. Also, notebook about nuclear transient and contamination. And I remember you that nuclear transient are not included in DP0, but there was this notebook trying to prepare a method if you can see variability within the nucleus of galaxies that might be hint for stellar disruption events or other kind of sources. Type 1a supernovae are included in the simulation. Here, I will not talk about it because there is a contributed talk later in the session, but we also prepared the analysis of the supernova rate within DP0. And then, also important, the sonification of light curves. There was an entire session on Wednesday about that. You can ask Riley Clark about details. I can also maybe show the sound. This is an example of type 1c supernova sonificated. And this is an ongoing project because Riley, Andres, Sara, and others were trying to install all the softwares with sonification within the Rubin Science Platform. And it is still ongoing because there was some problem with the requirements needed to install this software within this platform. But if you want to join this effort, you can just talk with them. And then we were also trying to prepare more advanced tutorials. For instance, we wanted to explore the difference image analysis because this is one of the hot topics for time domain. And there was a contributed notebook that I prepared some time ago that was explaining how to produce your own COAD as custom templates to run the difference image analysis and see how this is changing with the recovered light curves of the difference images. And last but not least, the fake source injection, which is still an even more important topic to include sources that are not included in the simulation. And we will listen talks about these things in this session. So I will keep it short. The future plans is to keep on building this more advanced tutorial. So if you want to join and participate in this effort, please join the TVS Task Force and also participate in the DP0 assemblies. Thank you. And now is Michael Wood-Vasey that is talking about difference image analysis. Michael, are you using your computer?
Sorry, I'm just finishing my bagel. They're all sure done.
Can I ask you a question while Michael gets set up? Is there like for the TVS DP0 Task Force, do you guys have like a GitHub repository or some place where you're collecting all of those notebooks that you're describing?
We don't have an official repository. Usually when we prepare something that become ready and important to share to the community, we just put it into the DP0 delegate contribution repository. Okay. We don't yet have our own repository because we are working on some other projects. But maybe in future, if you want to work on something bigger, we can.
Yeah.
But that's pretty good. Successful to everybody.
Yeah, I really like that.
Yeah.
Sharing through Zoom.
Oh.
All right. Good morning. It's Friday. It's again wonderful to see everyone, but I have to admit my brain is a little full. So I'm going to present some things that I thought were relevant, but I would really actually like to sort of pause after 5 minutes and hear what your questions are, because I think there's a whole range of people who have written half the tutorials to people who like just for the first time learned what DP0 was this week. And I'd like to do something of interest to, not so much the first crowd, but much of the second crowd in that continuum. So I'll start with, I think, a nice place to start navigating through looking at DIA objects, so difference image analysis objects. That's the table, that's sort of the summary table of the things found in subtractions and image subtractions. Now, the object, like in a static catalog, it's a little easier to think about what all those quantities should mean. What the same quantities for a DIA object, like where mean flux itself is not obviously what you want. I mean, you have to think about what that means for different classes of objects and all that. So it's a good place to start. And I wanted to go through this notebook that Melissa Graham wrote to sort of start thinking about and just get in your head is a nice place to start. Now, I will admit, it talks about supernova. So the next, after going through and talking about this a little bit, I'm going to take some of the same queries that you could do here and actually try to look at stars that vary in brightness. I don't think about them very much, but I understand that probably the progenitors to supernova vary in brightness at some point too. So I must be interested. I just haven't fully figured out how. I joke that scientifically, technically, I think it's super fun to think about these things. So when you run a subtraction, you subtract two images. Let's ignore all the details, say it comes out great. So then you have a difference image and you try to identify sources, positive or negative excursions from the template. Those are your DIA sources. Right, this is just the language, just the language. Sources are individual detections of individual things on an image. Objects are the coherent assembly of all those sources into a thing. And so this is what you measured when you ran the subtraction. You associate, hey, have I ever seen this before? And then you can go back and do force photometry, both at the individual images and the individual subtractions. Right, so if you have something that you didn't see it, you didn't see it, you didn't see it, you saw it at 3 sigma, then you saw it at 10 sigma, then you saw it at 12 sigma, then you saw it at 2 sigma. The DIA object is the thing that says, oh, here's my best estimate of the position. Let me run back and do the photometry to get both upper limits and more precise position measurements. For example, when we do detection in a difference image, we're going to detect 5 sigma excursions positive and 5 sigma excursions negative. We're not going to detect on 3 sigma excursions. That's not because you just have too many of them, right? If you think about 1 billion pixels in a Gaussian random field with some convolved with the PSF, at 3 sigma, most of the things you're going to find, or actually most at that point, are not astrophysical sources, they're just correlated variation. So we can't detect on that. But if we know that there's a source that did something interesting, that's a different statistical question, then you can go back and do the force photometry and then recover the flux variation around small excursions. Okay, so in particular, this notebook talks about some basic statistics that you would have for summary statistics. There are some more that are going to be calculated. And I think TVS is very interested in that. You should keep thinking about that. They're in the DPDD. They aren't fully filled out for DP 0.2. But simple questions. What's the faintest? What's the brightest? What's the average? Okay, sure. You can argue that, of course, extremum statistics aren't like good things, right? Because like the minimum and max is how many samples do you have, right? Like if you draw from a Gaussian and you draw 3 things, your min and your max are probably not going to be very big. But if you draw 10,000 things, you're going to actually sample the tails. So extremum statistics are theoretically not the great thing, but they're kind of useful to think about. But in addition to min and max, there are the percentiles. And this is the thing that you would want to use in thinking about what is that distribution and what's that telling you about it. And then the number of data points, the chi-square for what the mean is. So in this case, right, the chi-square is not, okay, it is the fit of a model, but it's a fit of a model we know is wrong, right? It's a fit of a constant model, but it's trying to quantify how off you are while including the uncertainties. Right, so the same, if it's nearby and bright, then small variations are significant because your signal to noise is very high. If it's much fainter, your signal is much lower, then that same astronomy is so difficult to talk. Magnitude of variation, same size of variation in flux space is less significant, right? If the uncertainties are higher. And so the chi-square is sort of calculating that thing. Was this deviation from zero significant? So for stars in particular, this is relevant, interesting. And then here's a fun little statistic, basically trying to say, incorporate the uncertainties and that Stetson came up with in '96, and to say I have a variable thing like a Cepheid, and I want to quantify something that looks like that without doing explicit like period folding or fitting or something like that, just a statistic. Okay. So here's just an example of doing a query. We're going to get those quantities, we're going to get some basic information, and kind of look and see what's there. So you might think that the the number of sources per DIA object, i.e. the number of detections that went into that, is correlated with the brightness. And that's actually kind of related to the previous point about excursions. And that's saying that the, as you get brighter, it's easier to detect, and you're going to detect the same source and more images. That's all this is really saying. But it's a reminder I like about the kinds of questions that you don't really ask about an individual image, but you might ask about the large sets that we're going to have here of subtractions. Okay, so this notebook goes on and talks about how to look for things that might look like supernova. And thinks about, okay, if I had supernova in some redshift range and I wanted to think about them, I have some model for what that would be, so I can figure out basically what brightness would correspond to a redshift range for supernova. So let me see if there are things in the DIA object table that would match this. So it takes the redshift range, it takes what is the peak magnitude of a supernova, it calculates the distance modulus, and uses this to a query. And we're not going to do cosmology this way. This is just a useful way of sort of trawling through and looking at things that might be supernova. And if you include these queries, so now this is sort of the same things we're getting, but now we've said, we want this quantity here to be greater than a certain amount and less than a certain amount. We're looking for some range. And here we are kind of interested in the maximum. Right? For the type 1a supernova that goes like this, maximum brightness actually does have a pretty specific meaning that is physically what I want to think about. And you can see the other bit that we had flux, and then here is the function that converts flux to an AB magnitude. The table doesn't store AB magnitudes, right? What's the AB magnitude of a negative flux excursion? Particularly for difference imaging, you really want to be thinking about fluxes, but we think about magnitudes when we think about stuff far away, just because a factor of 1,000 in distance is easier to think about as a factor of 3 or 7.5 and magnitude rather than factors of thousands. So here's how you construct such a query, and you try to find the things that are in range. And this notebook goes through and picks sort of the first best 20. You know what? They actually kind of look like supernova. They get brighter, they get fainter. We're looking at a couple different filters here, a whole bunch of different things. You can look at one particular case where here we've done the forced photometry. So this is saying for the 1, 2, 3 years prior, there's nothing. DC2 is 5 years, so 0.2 is 5 years. But here was the supernova, and then a year later it was gone. So actually this itself is clear evidence of probably some transient object, or at least transient on this scale. If it repeats, it's larger than this. So the way to that. Okay, so the notebook ends by saying, encourage you to think through other sources you might want to look at. And so I did a plot of that aforementioned Stetson J parameter versus number, this is number of detections. That's not like a deeply physically meaningful thing. I didn't want to pick the thing with 3 detections. I wanted to sort of think, something's happening out here. That's not the same as here. That's not the same as here. So I'm actually going to switch now to the portal aspect. So I find the portal aspect actually a little easier in some ways to do this. If I know the SQL query and I know the operations I want to do, I find it easier to write the SQL and do the joins. But if I just wanted to explore and say, hey, give me the light curve of this, give me the stamp of this, I find the portal aspect easier. So let me switch over to that. So we're gonna go ahead and get started. So first, we can do the same query that we executed before. So I've cheated, sorry, not cheated. I've come prepared, and this is the query that's already in there. So there's a UI assisted builder. This is helping you make the SQL query, but if you know what it is, and often very much if you can read someone's existing query and think about what the difference is, right? Perturbative analysis for code writing, that's pretty useful. So we're gonna take this query and we're gonna run search. Oops, we're gonna click. I didn't think that the part of the demo that would fail was my ability to click on a button. There we go. It's sending a job. Should come back shortly. And so down here is showing the table of all the results. So we capped this at 50,000. And this is all the columns we got. Each row is one of the things that came back. And in the portal, it says, you gave me a table, I'm gonna plot something. I don't know what you wanted me to plot, but if you have RA and deck, that's probably a thing you wanted me to plot. So here's RA and deck. And so this query is just showing you that was the RA and deck, and you can kind of actually imagine all the different images that went into this and how that ended up striped that way. Okay, but I said that I was interested in, excuse me, looking at the number of DIA sources versus the R Stetson J. Oh, this is not, I'm sorry, this is not showing up. I don't, okay. There are points here. There we go. If we zoom in enough, it will switch from binning automatically to doing the individual points. That's what this is done here. And so here are those different points, and I can click on one, and it will take me to that row. So I'm gonna go ahead and actually do a different way of doing this, and I'm gonna sort by this flux max. I spent that whole time making fun of extreme statistics just because I was going to totally use them and I wanted that awareness. Let's pick this one. So there's a big excursion, maybe the mean, I don't know. I have to admit, I don't know how to do this better. I'm just going to copy and paste this because object ID doesn't lookup doesn't work. Jeff, you may know how to do this correctly. Okay, it will, but I think a DP0 would work.
Yeah, I think it doesn't yet.
Yeah. Okay, and a funny little thing, you have to read this and figure out what you want. It's like, it's not super complicated. It's just not a question you expected. If you wanted the PVIs, the calibrated images, process is an image, but calibrated images, you want to click 2 here. Okay, and so, excuse me. So this has picked up an image that matches, and the thing that looks like a star to me. And sorry, there are 2 because I clicked on something else. We could also look at the subtractions. So for that, I want to click on 3. And if you want, you could now actually, you could click specifically on what product you wanted. And thank you for making this searchable now. Getting these names right was really difficult before, but we can do that same. You're noticing that we're getting an accumulation of tabs down here. That's just remembering for us the things that we're planning to do. And so here's the subtraction. And you can see the subtractions, these sources. And the stars subtract well, but not maybe perfectly. Let's go back to the catalogs and let's actually search, excuse me, for a different thing. And let's maybe go back and just do an easy spatial search. So here's the RA deck that I'm looking at. I'm going to do a simple cone search within 2 arcseconds. These are isolated stars, nothing's near them. So it's still showing me the image because it likes to show a thing there. But now it's returning that search that I gave it. This is the RA index for all the sources that came back. If you think about what these mean, this is just the spread and the detection of positions or thing. But again, RA deck isn't what I want to do. Plot, and here, Jeff, you may know how to do this better. We need to do a join to get MJD. I don't know how to easily do that. Assisted.
Greg knows how to do that, don't you?
Yes, I think that's right.
Anyway, but without knowing how to do that, visit at least monotonically increases with time. I'm not going to period fold to visit, don't worry. And so we're getting, this is showing all the filters. A variable star. So we could pick a particular filter if we want. We could go to filters and we could say a band. We want to be high band. You'll notice, for example, that what it does when you put in I is expands to like something I something, because there's I as the conceptual filter. Then there's going to be the specific, no, like this filter, not the one we dropped and broke last week. I'm sorry, but you know this filter. So this is a nice way of doing that. That's why it puts in the wildcards. And so here's the I-band like curve, which makes a little more sense, right? It's easier to interpret. Like this. That's a variable star. That's what I had. I just found it useful. Sometimes I do stuff in the notebook aspect, sometimes just futzing around in the portal aspect. And it took me a little practice to sort of clearly think about how to use these tabs and how they're saving what I did and then become that. Thank you.
Questions for Michael?
Yeah, I have a few. So I wanted to ask, how do you know, or is there even any difference between using DP02 images or DP02 catalogs, like which tab to use?
Sure, yeah. So let's see, I have a trivial answer, but I think let's build on that to figure out what the trivial answer is. The catalogs, you get the catalogs, and the images, you get the images. But are you thinking about like for what a particular kind of science investigation? Or what?
Yeah, so I guess whenever I was practicing using the Rubin DP02 tutorials, there were certain points where it would tell you to pick the catalog, and then other times it tells you to pick the image tab and work through that. So I just didn't really understand how do you know when to use each, because either way we're kind of like plotting graphs, if that makes sense. So I couldn't tell the difference between what I'm plotting.
Okay, so one of the confusions is, right, there are separate tabs to do here, like get images, get catalogs, get DP0.2. These are different tabs here. The results of executing a thing from a tab get put into results. So if I execute something else, that's going to put as another, I feel like tabs overloaded, or maybe it's tab, but anyway, that would get put another thing here. Then the portal aspect by default has table, plot, and image. So that's why it's a little confusing, because didn't I get this result by executing a catalog query? I did, but Portal really wanted to show me an image, so it just kept showing me the image it had from the other results tab. Thank you. I hadn't thought through that. That is confusing, because you had expected these to be separate, right? But if you step back and think about Portal's trying to help you integrate image and catalog analysis, but yeah, you have to build that model for how it's going to work. Greg, please.
Let me just add here that you can actually change the
Oh, yeah.
whatever the display is by clicking on a little something. I love the name of it, the hamburger.
Yeah,
Up on the upper left hand side, and you can Three horizontal lines
Three lines.
next to the
Oh, yeah,
Rubin
right.
thingy.
Yeah, and here you can set up your own display, you know,
bottom.
images, plots, whatever.
Thank you, right, so here you could like remove this, or I don't know how to add. but-
Just click the double, the up, down arrow. Yeah.
So they're pre-done templates to think about how you
Right.
want it. Thank you, that makes sense. And then for a particular one, you can expand.
So just as Michael said, the images is really something that the portal likes to give you, even if you don't want it.
So, thank you, Greg, that was a nice addition to that.
I have one, if nobody has. Oh, please go ahead.
I have a couple more quick questions. When we're using the shape, or like setting the shape as cone, I don't remember what the other shape was, but I just wanted to ask, why do we use cone?
Oh, as opposed to
The other
Polygon.
polygon, yeah.
a
sorry, I can't read
polygon,
that.
if you want to, I'm gonna answer the question of why is cone search the natural starting point?
Yeah.
Yeah, okay. Because positions have uncertainties. And I don't know that I'm gonna get that exactly. So when I ask to search, I'm gonna ask, oh, I understand your question. I'll get to it just a moment. Okay. So I'm gonna search in the sky to a certain point with some uncertainty annulus. The reason that's a cone is because we see projective sky in 2D RA deck, but it's from a volume. So a specific circle ellipse intersecting, you know, our projected sphere in distance is actually a cone. So that's why we call it cone search, even though it's RA deck.
It's also the only one that has one parameter. Because polygon has multiple parameters, right? So it's the simplest one here.
Yeah, yeah. But I think the question was, why do we call it a cone search when it isn't a circle on a sphere?
There is something on the Slack channel. It's not directly, Howard, it's not really related to Michael's talk. It's more of a comment from Jungi Rowe. He says, as I mentioned during my question, making a Slack page for each science collaboration science group would be a good idea. Right now, each group has its own system and takes time to see what they're doing. My science interests are across many astronomy fields, and I want to explore what I want to do, anything that inspires me. For the science papers, this is a suggestion for the LSST management. So yeah, it was not really, it's more, I think, more from the earlier, from Vincenzo's talk.
Yeah, I'll let you get this one. I feel like Jungi's question is relevant to TVS in particular, which is an assemblage of all sorts of different interests under an umbrella.
I see Sara as an hands up. She wants to say.
Oh,
Please go ahead, Sara.
Yeah, yes, thank you. Can you hear me?
Yes.
Okay, thank you. Yes, maybe I can address this question because on LSST-C workspace, there are Slack channels dedicated to each science collaborations, and within each science collaboration, I can talk about what I know best, like transient variable stars. There are specific Slack channels dedicated and focused on our subgroups, which mainly focus on scientific topics. So just to mention a few of them, supernovae, fast transient, or pulsating stars, or non-degenerate variables, or focusing on the task forces, like this one Vincenzo was presenting, the task force of TVS, focusing on the activities related to data preview 0, and many more, like task forces on crowded field photometry, or task forces on survey strategy optimization. So I invite everyone interested in joining the TVS, and then some specific subgroups or task forces there. And if needed any additional information on the ecosystem or of the science collaboration, please don't hesitate to contact me as a co-chair of TVS and Igor Andreoni. So I don't know if this answers your questioning your suggestion. There are some resources already available there, but please contact us if you need more information on the many activities of the very diverse range of scientific topics concerning transient variable styles, at least. So I can talk mainly about that. Does this answer your question, your comment, Jongi?
Yeah, I'm not limited to TVS group. I'm also interested in galactic plane survey. You know, I'm working on also diffuse emission and star formation. So I think I'm just to see the way you could do in Slack page. One is, you know, DSC, one is TV group, one of galactic plane. So, you know, have a chance, users have a chance to have opportunity to explore and see each group where they are in terms of, you know, their planning for papers or science ideas.
Sure, the best way to be more engaged in that, as Federica was suggesting also during the plenary, is to get in touch with the science collaborations. Myself, I do work also on galactic plane science, and so I'm a member of both TVS and Stars Milky Way local volume. There are some task forces that are shared between two science collaborations, like, for example, the crowded field photometry on TVS and Stars Milky Way local volume. And we also plan to organize in TVS again a sort of onboarding to show new members or members that would like to be more engaged in the future to provide an overview of all the subgroups, task forces, the contact person, the activities ongoing, and the scientific topics leading to publication. So definitely, please keep in touch. Yeah.
I'm sorry to interrupt. I see another hand on, but we should move on. And we plan to have some discussion at the end of all the presentation. So thank you again for this discussion. And our next speaker is Jeff Carlin, who's going to talk about injecting variable sources into multiple images. Please go ahead.
Yeah, so this notebook, I'm just gonna go through a rendered HTML version, not a version on the Science platform, but you can execute this in the Science platform at your leisure. Let's see if I can find the right thing. Don't worry, I'm not gonna go through all of the tabs in my browser here. That'd be ridiculous. This delegate contributions DP0.2 repository is a place where, like Vincenzo mentioned, you know, people from the community, people from different science collaborations, when they develop a notebook, can contribute this so that others can benefit from the explorations that you did. Who knows, you might even meet new collaborators, fun stuff like that. In this case, sorry. In this case, the notebook that I'm going to talk about is in this source injection folder within this repository. You can see there are two notebooks. One about if you inject synthetic galaxies into an image, how can you make sure that they're all aligned from one image to the next? And the other is this injecting variables, which is what we're going to talk about now. And it was, as was kind of alluded to by Vincenzo before, that you know, the reason you might want to do this is because the data preview 0 simulations are, you know, didn't simulate every astrophysical object in the universe. It's a limited set of simulations. So if the type of object that you want to study isn't there, one way to sort of test your algorithms and learn more about how well you'll be able to do your science is to just inject synthetic sources into the data. And so that's what we're focusing on here. And this is using, if I can find the right tab, there we are. This is using package in the science pipelines that is called source injection. So this shows you an example of an image before and after injecting synthetic galaxies into the image. So you can see it's flashing between the two. There's even a, if I can find it, it'll take too long. I think it's here. You can inject the Rubin Observatory logo if you want even, but you can inject point sources, you can inject galaxies parameterized by a variety of different parameters. You can inject, like that logo, you can inject an image into the image, like a postage stamp cutout image into the image. So if you had, say, a simulation and you wanted to extract the image from that and put it into real or DP0 data, you can do that. And so what I'm going to show you is, sorry, this is getting in my way. What I'm going to show you is how to inject a variable star. In this case, you'll see it's a really toy model of a variable star into a series of images with the correct magnitude corresponding to its variability. So you can see here at the beginning, we load a bunch of packages. Most important for this case are these two lines here with the source injection package. Is this big enough? Can people read the text okay? Yeah, good. And then we define a few simple functions to create cutouts from images, and this is my toy model of variability. This just creates sinusoidal variability. So you can see it just takes the period in days, the amplitude and magnitudes, and the mean magnitude, and then gives you back the magnitudes at the midpoints of all of the exposures you're interested in injecting into. So that's what we'll use to calculate the magnitude to put into each image. And so the first thing we do after we've initialized a butler, which I won't go into what the butler is, but it's the way of managing data sets in the science pipelines. So the first thing we want to do is we want to say, I want to inject a star at a given position on the sky. So we need to find all the images that overlap that position on the sky. So we pick some right ascension declination. I think this was totally at random. And we do a little bit of gymnastics here to go and find from the butler all of the CalEx images. These are the calibrated single visit exposures. We want to find all the CalEx images observed in the I band that overlap this position on the sky, which in here is parameterized by the HTM is hierarchical triangular mesh. It's a way of dividing up the sky. So we used some functions above to figure out which one of those trixels on the sky this corresponds to, and now we're going to find all the CalEx that overlap that. And you can see here, when you do that, you find that there are 137 images that overlap the position we're interested in. So then the other thing we need to get the variability right is the time that each exposure was taken. So for that, we go to what's called the CCD visit table. And we use all of those references that we retrieved for all of the images to look up from this CCD visit table, this exposure midpoint MJD. That's the time of the midpoint of the exposure. And once we have those, then we can simulate our light curve. And so you can see these are in units of days. And so then we use that function that we defined to create some sinusoidal variable with, in this case, a period of 100 days, amplitude of 3 magnitudes with a mean of 20. So it's totally not a realistic type of source, but this is what it looks like. This is the sinusoid overall, and each of the points here is one of those visit images. So in this case, we're just going to focus on the first, basically the first period of this orbit, and just pick those red points to inject into. So now we've calculated what magnitude we need to make the star that we inject into each image to create this type of variable. And so then we just put that, those exposure midpoints and the magnitude that we want to simulate at each one of those times into a table. And then you can see here, now we're going to use that table to inject a star with those properties into each of the images corresponding to that position. So here we have this visit inject task that you can see here. And its configuration. You can edit configurations to change how it behaves, but we're going to keep the defaults. And we just initialize that task. And then we loop over the visits. And for each one, we run that inject task. So right here, you can see we send the results of that inject task to this injected output. So for each image, we send it the entry from that table corresponding to the image that we want to put it in, and we send it the image, the point spread function of that image, the photometric calibration object corresponding to that image, and the WCS, which is the mapping between pixel and sky coordinates. And when we execute that, it gives us back an exposure with the star added to it, the artificial star added to it, and we can also retrieve the catalog of things that we injected just for future use. And then we have to do one additional step because a single visit image can be taken at any orientation on the sky. So, you know, images can be rotated relative to each other. And so this next step, this warp image part, is just to warp them all to a common orientation. So that you'll see later, they're easy to compare to each other. And when we execute that, it prints a bunch of progress to the screen, tells us, you know, I'm injecting one source in each image. And when that is done, we have a whole bunch of images. And so then the last thing I wanted to do here is just to plot little postage stamps of these images just to see, does it look like it is a variable star, you know, with the correct magnitudes? And so so all of those images I injected into are shown here. Actually, I'm gonna zoom out a little bit because now it's hard to see when I'm zoomed way in. There we go. And you can see that for each of these images, it has the exposure midpoint, and it has the magnitude of our simulated variable star. And so you can see, for example, it's easier if I scroll down a little. So like here in this row, you can see this is magnitude 21.6. It's this fairly faint star in the middle. And then at this particular time, the magnitude is 18.4. And so you can see the same star is much brighter. So I think it's successfully doing what we want. This notebook stops right there. But of course, you could then go on to say, all right, now what if I want to run, source detection and measurement algorithms and test how well I can recover this? And of course, scientifically, it's not very useful to inject a sinusoidal variability, but you could simulate, with any function you want, that variability. It could be like an RLI variable star. It could be any type of astrophysical object you want. So this sort of just shows you how to do that for all of the individual images. The one other thing I wanted to mention before I wrap up is, oh my goodness, sorry, too many tabs. Is that there is also a more general overview to the source injection tasks in this data preview 0 notebook 14, I think it is, that goes through in detail, injecting, for example, I think injecting a postage stamp of a galaxy image, injecting, I'll show you, a random set of weirdly shaped galaxies. And there are some injected stars in here too. So if you want to know more about the source injection package more generally, this is available in your notebooks, tutorial notebooks directory in the science platform. And I'll wrap up there. Thanks.
Please come to this side of the room.
I imagine it's probably not the best idea, but instead of injecting into an image, could you directly inject parameters and stuff into object or source tables?
Absolutely. Yeah, in fact, there's a detailed study that I'm a collaborator with the author, who's an undergrad at University of Chicago, who's done exactly that, where he wanted to test how well we can detect faint dwarf galaxies around the Milky Way. And so he just injected, simulated dwarfs into the catalogs and did those tests. So that can be super helpful if you don't necessarily need to go directly to the image to get, like for a variable star, for example, you may not need to put it in the image and go do all the processing again. You could just put it directly into the catalog. So yeah, that's totally an option, and it would be fairly straightforward to do, because when you get back a catalog, for example, from the Butler, it's just an AstroPy table, so you can very easily add things to it.
Chance a notebook like that doesn't exist, right?
I don't think so, but it's a good suggestion, so I will make a note. Thanks.
Other questions?
Maureen's had her hand up for a
Yeah.
while.
Oh,
Yes, hi, everybody. Hi, Michael. I have a question from also your, so first of all, thank you so much for all your work and these presentations. As some of you know, I've been, also in the field, but right now is obviously a great way to get re-involved. So I have a few questions. So one is for Michael. So for 1As, right, you showed the nice light curves. For also other types of transients, like core collapse and so forth, that and fast transients that in at UVA now, those would be picked up by brokers, right? We'll be relying on those. And I know that during the ComCam there will be no alerts because of various, I guess, constraints from national agencies. But there was a dress rehearsal with various brokers. And so I'm curious to hear, since Michael, you also have, right, you and others have the pitch. Well, how, they sent things over, but did you actually run your algorithms on the data? And was the data stream, getting ready with, this idea of getting ready, and, DP0 is obviously in various other, one way, but then for, the transit community that relies on alerts, I didn't hear much in the sessions I went to about how, ready the brokers are. And whether they ran, the algorithms on it to see, you know, whether the kind of the level that of performance that is going on right now on, you know, ZTF data and others, if that's still, you know, if that is something that's happening. So just one question. The second one is about, you know, injecting and, you know, so something that was mentioned was that, you know, you mentioned force photometry, right? For objects that we know. And then in the LSST data, what about cases where, for example, a transient goes off that was not detected by LSST because it was just looking at the other part of the sky? I mean, obviously still in the south. But what we want to see pre-explosion outbursts, because it turns out lots of these core collapse have outbursts and so forth. So would that be provided? Because I remember Melissa said there will be 30 days of force photometry kind of saved, or if not up to a year for objects that LSST triggers on. But what about those that are not triggered on? So there are two questions. Sorry if I took a lot of time. I think it's relevant for, you know, also to other people. And again,
First question, the brokers, do they actually produce useful results?
that's your rewording.
That is my wording. Ours does not mean it that way. One answer is several of the brokers are running on ZTF right now. And you can look at those outputs and figure out how that maps. The second answer is the Elastic Challenge definitely has things that looks very much like the alert packets, and the effective information from the object table and the source detection that are in there and those classifications. Now, however, brokers varied in how much they tried to do a good job classifying the results for Elastic. I think that was, again, most of us thought about that, or at least we did, as an infrastructure test to make sure that came all the way through the test. So I think your broader question, Mariam, is very timely. Like in the next year, it'd be very, very helpful to understand if the brokers are generating good classifications for things that really look like LSST data. I think we sort of do have that gap a little. Having said that, I think you can definitely take the results of DP0.2, a person could, and the DIA objects and the DIA sources, and go run whatever classifiers you think would be good. And I think that is a study that could happen, even though DP0.2 didn't generate alerts, like the conceptual information is in there. Now the templates are not necessarily like from some controlled time period, they're just sort of whatever. So I think your question is good, Mariam. I think that takes some effort. It is timely, and to be frank, the management and oversight of the brokers is confusing due to their key role in the Rubin ecosystem. Sorry, Rubinverse. Who said that the other day? I'm going to use that. But yet they're being outside the project and operations. So I think you're right to answer that question. What was the second, Jeff? Or Mariam? But
yeah, we can talk offline too, because there would be ways to get funding, right? I mean, you are on LSSTDA, right? So we could think about ways to work on that. So the other question was about force photometry. How long? I mean, I think said that. Oh, sorry. Did other people have questions? Sorry, I didn't want to.
Thank you. The force photometry. Yes. So that won't come out of Rubin operations or the alert stream, but a person could totally run that on the RSP. The images will be available within 80 hours afterwards, and you could go do your own force photometry to get upper limits on both the individual images and on subtractions that had been run and existed. But that would be a thing a user would have to separately do. But a user with data rights could do that in the RSP.
Okay, great. Thanks so much.
Thank the speaker again, and so Michael. Speaker is Ake Vitanen, that is going to talk about the simulated AGN catalog. That's great.
Okay, thank you, Vincenzo. So I'm a postdoc working in Osservatory Astronomy at Roma, and this is kind of like parallel to what Jeff just said, a parallel approach. So this is a part of an official enough in-kind contribution that we mostly work in Roma, and then also collaborators in Italy and abroad. So since we have a diverse audience, I will start with the working definition of an AGN. So we know that there are supermassive black holes in virtually every massive galaxy, and we know that most of them are dormant, most of them are not active, so 5 to 10% are, and then we can see the AGN signatures, such as non-thermal radio or X-ray gamma ray emission, or then what is relevant for LSST is the bottom 3, so basically non-galactic emission in the optical UV, and especially variability. And current simulation status in LSST, as you may or may not know, we have absolutely no AGN in DP0. So in the AGN science collaboration, we have a big need to actually have these simulations. So what we try to do, so we have produced this pipeline, which we call Agile or AGN in the LSST era. And the idea of Agile is to mimic something that was already done in the DP0. So the idea is you start from the left-hand side of the plot. So we start by creating a truth catalog containing galaxies, AGN, and stars. Most of the work we have done is in the AGN catalog. And then the idea is to feed this truth catalog into the image simulation, like it was done in the DP0, and finally analyze the simulated images using the LST science pipelines. And to start off, I go a little bit over the details of generating a truth catalog. So to get the galaxies, we use an external code, which is called an empirical galaxy generator, or EGG. And what EGG does is that EGG takes a galaxy stellar mass function. We use the Cosmos 2021 up to redshift 5.5. And basically EGG solves the question of, okay, if this is stellar mass function, what are the physical properties of the galaxies that correspond to the stellar mass function? So from EGG, we get a realistic galaxy population with star formation rates, redshifts, morphologies, and everything that we need for the rest of the simulation. For the AGN part, we start by painting AGN on top of the galaxies. And for this, we start from the basically from the X-rays. So we start by adding accretion rates to the galaxies using observational results. So this is the probability. Every galaxy has a probability of hosting an AGN with a given accretion rate. And this is as a function of the host galaxy stellar mass, redshift, and galaxy type. So we take into account also the morphology. So basically each galaxy in our simulation has an accretion rate, and only some of the galaxies have an accretion rate that is above a threshold, which we then call an AGN. We then move from the X-rays to optical by using recipes. We have a conversion between the X-ray luminosity and the UV luminosity. We assign a type. We have type 1, type 2 AGN in the truth catalog. We assign an EB minus V, so we redden the SCD of the AGN. And finally, we assign an SCD to each AGN created this way. And this is an example SCD from the simulation. So here you can see the galaxy SCD in red, and then you see the AGN SCD in blue. This is a type 1 AGN, so basically a quasar. And then the combined SCD of each object created this way is just the sum of the two. And here you can see also the LSST bands. We can, in principle, add any filter curves into simulation that we want, but LSST is the focus for us. So then we have the AGN catalog out of the way. We have the galaxy catalog out of the way. What is missing is the star catalog, for which we are using another external contribution. So this is another in-kind contribution, which simulated in the LST context, Milky Way and Magellanic Cloud stars and binaries. So we just take this catalog at face value and add it into the truth catalog that we have. And if you would like to access this truth catalog, we have created one that is 24 square degrees large. So we put it online. So if you will find it in the repository that we have hosted online. And this is a subset of validation that we have done. So this is looking at the optical B-band number counts of the quasar sample in the truth catalog. On the left-hand side, these are data points that we took from the LST AGN science book. And then you can see the line that the type 1 AGN or the quasar sample that we have in the mock. And then we can also, we have also looked at the redshift distribution of this source. So basically look at the quasar luminosity function, which is on the right. Then this is a static universe. So we add on top of the static universe variability in order to add basically a time coordinate in the simulation. So for each AGN, we add a light curve using a model which is called the damped random walk. The damped random walk model has exactly 2 free parameters, and these parameters scale as a function of the AGN properties, like the black hole mass, for example. Here I'm showing a couple of damped random walk light curves as a function of the absolute magnitude. As detail, we have another recipe for type 2 AGN where basically the variability is just lower. The amplitude of the variability is significantly lower. We've added a recipe for optical variability for stars. So basically for long period variables, classical C fates and eclipse in binaries. This was basically given to us, and we have just implemented it as a part of the pipeline. So this is the chart. How do we then simulate the images? So now we have the instant truth catalog with fluxes varying over time, and then we get the sky conditions, telescope conditions, everything LSST related directly from the baseline. And we feed all of this information in the IMSIM, which is the same software that was used by DESI in the Cosmo DC2, in order to create single visit 30-second exposures in any of the LSD bands. And up to now, we have a small subset of simulations completed in the Cosmos. So this is about 1,200 visits, single detector. And this is what we can do locally at our cluster. This is the scale of things. Here is an example image in all of the 6 bands in the LSST. So this is a small zoom in of a single detector with all of the bands, with all of the six bands. This is an example of an RGB image. So on the left-hand side, you can see a single detector, which is 0.05 square degrees. And then on the right-hand side, again, a zoom in of 9 arcane square. This is how the light curve plays around with the image simulation. So at each date, when we have the single visit observation, we go ask the truth light curve for each of these AGN, what is the current flux of the AGN? And these are image cutouts taken, these are all R-band images, and these are image cutouts taken at these dates, which are given by the light curve. So here in the light curve, the black points are the LSD cadence in Cosmos that we are simulating, and the solid lines are the truth light curve. So basically, we can simulate any date we want, but at the moment we are simulating the LSD cadence in order to be as realistic as possible. Finally, we feed the images into LSD science pipelines. So before the conference, we had done like a single image processing, getting the calibrated exposures, the source tables, and during the conference, I was able to also run the whole science pipeline. Thank you. So the whole science pipeline. So we also now have forced photometry, the IA objects, and also the whole difference image analysis and detection from that. There is also something to be done for the automatic truth catalog matching, which is still something that is on the way. Here is one extracted light curve combining it all together. So this is again an example AGN from the simulation. And then here in blue, you have the truth light curve that we are simulating. And these are 2 different outputs from the source tables that we get. So one for the PSF flux, one for the Calib flux. We are having a discussion at the moment, what is the best flux measurement for AGN, because we have different levels of post-galaxy contamination. So sometimes PSF flux works for QSO type objects. Sometimes Calib flux could be the better measurement for the flux. This is a list of features that we have in Agile at the moment. The most important thing is that we're aiming for first release somewhere in September, October by releasing a 24 square degree mock catalog, and then plenty of more simulations visits in the Cosmos field. So we're aiming for a 1 square degree field in Cosmos, and probably the first 3 years worth of visits in Cosmos. We have put the demo in the RSP. This is available for anybody. You can copy over the notebook, you can run it in RSP, and it will run you through the output products that we have currently. So playing around with the truth catalog, the Galaxy images, the source tables, and hopefully it's usable. I have it open right over here. So it tries to be as helpful as possible. And because of size limitations, we have a limited set currently uploaded in the RSP. So this is, we have 10 observations, basically 10 visits, the corresponding Galaxy images, the corresponding source catalogs. And this notebook explains to you how to play around with the truth catalog, and then also how to plot different AGM properties, for example, from the truth catalog. We are also explaining how to plot the SCDs, how to plot somewhere here, we have the Galaxy images as well. So how to plot the Galaxy image, the object in the Galaxy image, so on. So please, if you're interested at all, please copy over the notebook, go play around with it, report to us, whatever you find. We are open to receiving feedback, and we would like everybody to use it as much as possible.
Thank the speaker. Questions?
That's awesome.
I agree.
When you paint your AGNs in your Galaxy sample, do you have any clustering constraint in the sense that, I mean, there are several studies that shows the probability of a galaxy to host an AGN is a function of clustering of environment. Is there any recipe or any plans to include something, or is it just random?
Yes, it's on the list of features to be added, because this is my background is AGN clustering, but at the moment, what we have in the simulation is that for the galaxies we have a very light clustering receipt. So how the galaxies are distributed in the universe, it reproduces the two-point correlation function to some degree, and we would really like to do this for the AGN. That the AGN clustering also reproduces the two-point correlation function, but at the moment we don't have this in the simulation. But it is on the feature list that we should eventually add.
Other questions? I do have one, which is good for Ak and also for Jeff and Michael if they want to answer. So would it be possible to test, these are variable sources by definition, for extremely obscured AGN, how the difference image analysis algorithm is going to detect variability, and the fraction of bogus detections or artifacts that is going to be detected on these sources. Do we have, I don't know, matrix flags or residuals in the different images as a default products from the data products of LSST?
I think the literal simple answer is yes, but that doesn't translate into knowing the answer to the question you wanted to know. So would it be possible? Yes, but I think it would be great to basically combine those two talks of injecting those and injecting a range and seeing what the recovery is and seeing what the recovery is versus a certain purity. Obviously, if you don't care about purity, you can just take any one sigma fluctuation and that counts, but clearly that's not quite what we mean. I think that'd be super interesting. Yeah.
Yeah, and it might take a little sort of poking around to figure out like what the flags or the parameters are that help you identify those.
But you can start with like just the trivial, like just do one.
Yeah.
Then just do 10 in an image and just like get your head wrapped around and then have something that we can figure out if running at scale makes sense.
Okay, thank you. No question. Let's thank the speaker again. So that speaker is me for the very last talk of this session. And we'll talk about type 1a supernova to discover the projection to the rate with DP0 and trying to go beyond. So the problem of the progenitor of type 1a supernova is really interesting because we all use these sources for cosmology, but actually we don't have a clear, unambiguous evidence of the progenitor. So there are two main progenitor scenarios. We know that it could come from a single degenerate scenario of a single white dwarf accreting matter from a non-degenerate star, or there might be two white dwarfs orbiting together, spiraling, and eventually merging. So we don't have unambiguous evidences. There are many ways where you can try to answer to these scientific questions. But to measure the supernova rate is one of this method, because from a theoretical point of view, you know that the rate is just resulting from the convolution of the star formation history over the whole galaxy lifetime. And then the distribution of delay times. What are these delay times? Is the time that is required from the very beginning, the formation of the binary system, to the final explosion. And there are, of course, constants that are needed to put together. So what is the point? Is that different delay times are related to different progenitor system, as you can see in this plot here. So there is SD for the single degenerate, and there is two possible double degenerate scenarios that depend on the initial distance of the binary system. So if we can measure the supernova rate, and we have information on the star formation history, and we have models that are related to the progenitors through the delay time, we can try to see through the measurement of the rate if we can distinguish between the scenarios. And in this plot here to the right, you can see the supernova rate as a function of the specific star formation rate. And all these lines here are the three different models of the progenitors. As you can see, in principle, it is possible not over the entire range. In some ranges, the models are more divided, but the problem is the uncertainty that you have on the single measurement. You can do something similar also with just the rate as a function of redshift, the volumetric rate. And this is a plot that is putting together the line again are the models, and all the points are the points over the past 20 years of actual supernova surveys. This is not updated yet because I should add the recent dark energy survey points. But you can clearly see that the uncertainty that we have on the points is really making the problem here. So it will be interesting to understand if with the upcoming LSST that is going to detect lots of supernovae, we can reduce these uncertainties and you can use this method. And in this theoretical work here, you can see that these bands here are the uncertainties that you expect on the models. That depends on the uncertainty that you have both on the cellular evolution models and also on the star formation rate that you can measure. And these points here, the blue and the red one, are the expected statistical uncertainties coming from LSST, which are way lower than the uncertainty that we have on the model. But of course, it is not just about statistics. You have other sources of uncertainty that are contaminating your measurement, and some of them are listed here. We have the survey strategy, of course, and this is why we have a lot of metrics to understand what is the better one to study the supernova rate, the detection efficiency, photometric calibration, the artifacts contamination coming from the subtraction. And there are also photometric redshift, the accuracy that you have from redshift, the association of transient plot galaxy, and last but not least, the photometric classification, because we cannot have spectra of all the sources. So what I tried to do using the DP0 is to focus on the last three of them. So it was a project that was also part of was done within the dark energy science collaboration. So we started from a sample of supernovae over 15 square degrees of the simulated DC2 universe that was selected by Sanchez et al. In 2022. And so this sample is containing 600 supernovae, type 1a supernovae, that are observed in at least 5 distinct nights. So we started with these supernovae. They are all type 1a because there is no contamination. And we tried to measure the rates, just pretending we don't know what the sources are. So as a first thing to do, you need to associate the transients to the host galaxy. And the sources, the supernovae in the DC2 simulation are associated to the galaxy, and the probability of the occupation is just proportional to the stellar mass. And it is tracing also the light profile of the galaxy. And there is no correlation between the supernova type and the host galaxy properties. So we decided to design a method which is the directional light radius that was used also in other past surveys. And in particular, we adapted the method described by Gupta et al. 2016. This method is consisting of ranking the best host candidates using the angular separation, but also the orientation of the galaxy with respect to the transit. And we prepared a code which is publicly available and was also tested with the Rubin Science Platform. So if you go to the paper, there is the GitHub repository where you can download and test the code. And it is producing you cutouts like this. And when you run it, you have a table with the best ranking sources. And there are also numbers popping out on the cutout that are showing what are the sources. And of course, as DC2 is a simulation, you know what is the true host candidate. And so we can test the efficiency of this method. And it is 89% correctly associated galaxy, which is maybe not a lot, but you need to think that it's a very easy code. It's not machine learning based, it's very fast, and it's giving you a benchmark that is not having as input information on the transient itself, because there is no correlation between the transient and the host. So you can use it as the beginning point, and then use a more complex algorithm later. And of course, it's better than using just angular separation, because it is 80% in that case. Then we used a catalog of photometric redshift that again was computed by the Dark Energy Science Collaboration using a training set up to magnitude 25. And here you can see the plot, the scatter plot with photometric versus spectroscopic redshift. And the mean uncertainty is 0.05, and there is a 7% fraction of outliers. But the problem of photometric redshift with the rate is that this is changing the distribution of the object as a function of redshift. And as you can see in this histogram, the black line is the true distribution of the simulated supernova. Then if you look at the green one, is the distribution by using the photometric instead of the true redshift. And you can see that the supernovae are moving in the different redshift bins. And if we put also the effect of the association of the host galaxy, as you have a misassociation, supernovae are still moving into different bins. So we have this spreading of the distribution that it is going to affect the measurement of the supernova rate as a function of redshift. So it is an effect that you want to take into account. And then there is classification. We tested different methods. First one is a PSNID, which is a Bayesian template fitting method. We also tested just a fit of a model that is used for type 1a supernova, which is the SALT2 model. And these two models are publicly available through the SNANA package. And this package is not included in the Rubin Science Platform, but it is possible to install via the pip install, and you can just run it on the RSP. And then we also tested supernova, which is a recurrent neural network that was trained on the elastic simulation. And here you can see examples of performances that, of course, depend on the prior information. You can write it without prior redshift, using the photometric redshift as a prior, or the true spectroscopic redshift, which is giving you the highest result. We used the PS90 with the photometric redshift as a prior, because this is what you are going to get for a truly photometric survey without spectroscopic information. And of course, you need to take into account that this result, this 95%, is a little bit biased, because in this situ there are no other contaminants. So truly all the sources were just type 1a. So the effect is that you are missing sources from the catalog. So now the effect that we can try to look is looking together separately at this effect, the photometric redshift, the photometric plus misassociation, and then also the effect of the classification. You can try to quantify how many supernovae you are losing from the original catalog. And in this graph here, you have the lost fraction as a function of redshift. So how many supernovae you have less with respect to the original one. So it is just the difference between detected and recovered, normalized with the number of detected supernovae. And the mean lost fraction is around 17%, but the greater effect here is photometric redshift, because it is the very first step, and it is also affecting the photometric classification when you use it as a prior. So when you try to measure the rate, the point is, of course, that using points that are coming from the different subsamples, you are getting different results. And so if you try to fit a power law resistance as it is here, you are going to get different values. And so if you want to use this as a method to constrain the progenitor, this is an issue. And it is important trying to reduce this source of uncertainties. Now, the very real thing that you will get from a survey is the case where you use the sample of supernovae properly classified using the photometric redshift of the galaxy that you associate. And this is the points here that you see. They also have uncertainties now, which is mostly coming from the statistical uncertainty. And all the gray points on this graph are the points coming from the previous plot that I was showing from the previous survey. And what you can see is that, of course, the uncertainty now is lower. So this is what we expect from LSST because the sample is way larger. But still, we have these uncertainties that are not really allowing you to distinguish between the different progenitors. Now, it has to be said that also the volumetric rate up to redshift 1 is not the best way. It would be nice to look at the rate as a function of galaxy color or subformation rate, but this was not really included in DP0. And the other problem was the lack of contamination effect in total classification. So if you want to go beyond, which we need to do, is to go beyond DP0, which is what I was trying to do right now. To do that, you can take different pieces and put them together. On the one side, you have theoretical models. You have models for the distribution of delay times associated to different progenitors. You can use a simulation having a galaxy sample with subformation history, masses, etc. And so you can have the expected number of supernovae happening each of these galaxies. And then on the Rubin side, well, you have the Rubin cadence. You can use the latest baseline as a reference. You have the throughput filters. We can develop K-corrections, and you can use observed supernova templates so that you can try to produce what are the real observed light curves. And if you put everything together and you try to measure the detection efficiency, you get these observed light curves, you can try to understand what is the effect of the recovered supernova rate, putting everything together. So on the Rubin side, if you use the latest baseline, you can define just a very easy metric that is returning you all the observations given a certain coordinate. And this, for instance, is returning all the observations that are centered on the cosmos field. And it is producing also these maps here. But the important thing is that you can get observation in the same field for the different filters, and also the 5 sigma depth magnitude that you can use as a reference to get something related to the photometric uncertainty. You can put this information together. You start from observed template for different supernova types. You use the K-correction to adapt everything to the LSST filters. You get information of the photometric error from the OPSIM, and you can get something like this. This is an example of a type 1a supernova at a redshift 0.3, as it should be observed by Rubin. So you can simulate tons of these sources, you can put them away, and now you want to understand how to put together to measure the rate. So first thing, to measure the rate, you need to take into account the sampling effect. And you can measure this sampling effect via the control time method, which is just a sort of effective observing time that you can use to detect your transient. So what it is doing is just taking the real observing time, which is 10 years for the entire LSST, and this is proportional with the detection probability of each supernova that you can detect as from detection efficiency. It is actually the complement of the probability of non-detection, because if you do that way, you can understand that if detection efficiency is maximum, is 100%, then of course this is 1. So it is counting as an object that you can detect. So we're using the detection efficiencies as a function of magnitude that were calculated by Sanchez et al. In the paper that I already showed you before. And doing the calculation, this is an example of the effective control time for type 1a supernovae, and they are observed in the cosmos field. And of course, what you see is that at redshift 0, the supernovae are so bright and so close that, of course, the effective observing time the entire cyber duration, and this is going down as you proceed to high redshift. On the simulation side, we're using a simulated universe that was prepared by Carlin in 2023. And it is providing information about the rate per galaxy, and the star formation density for this simulated universe is coherent with what is reported in Maddow and Dickinson 2014. So as we have all the information for the different progenitor model, you can plot the rate, for instance, as a function of the specific star formation rate, and as a function of galaxy color. And you can see that there are regimes where you possibly could try to understand if you can distinguish between the progenitors. And these are just examples of true observed rate with the uncertainty here on this side. And these panels are just distinguishing the regions of passive star-forming and starburst galaxies. Now, this is still a working project because now we need to put together all the other information. This was only taking into account the statistics and sampling. Now we need the effect of the host galaxy association. And from my previous work, I know that it might be up to 10%. Then there is the effect of photometric redshift uncertainty. And an idea could be to take it from the recent DESC application. As you can see here, this is a paper that is reporting the uncertainty as a function of redshift. And there is also the classification efficiency. An idea could be to take it from elastic, and this is one of the recent paper analyzing elastic simulated light curve. So I stop here, and as this is a work in progress, I'm very happy to get your feedback if you have on how to proceed with this work. Thank you very much.
Before you take questions, we're gonna need to take that laptop soon, send it back. And we got flights to catch.
I'm curious, since this is totally not my science field, I'm curious, I guess, how much additional uncertainty how do you have a rough idea of how much the classification efficiency and the redshift uncertainty will reduce your
I only have an
efficiency?
idea based on what I did with DP0, but that was very, very biased. And so the effect was to lose sources in the sample. But actually it is more complex because I'm not just losing sources, I'm getting wrong sources that I misclassify. And so the effect, for instance, for redshift is very easy. So you can put a supernova into the wrong redshift bin. And so this is changing your rate. For classification, it is happening the same, especially type 1bc supernova. You may misclassify them as type 1a. And so everything is mixed together.
So it's not just like reducing the
It's not
efficiency,
just
it's all-
reducing.
yeah,
It's a
okay.
combination of effects, and it's not easy to discriminate between these effects. That was part of the idea of this work. Try to understand how to correct the effect when you measure the rate. They need the computer. So if there are no other questions, thank you again for joining this session. I hope you enjoyed the meeting. Thank you very much.